Hello, welcome back. In this video, we're going to learn how to prove statements by using the proof by contradiction method, which is based on using the negations of given statements. Let's see how. Before we start though, let's go over the definitions of a few terms. When we're talking about a statement, we're talking about a sentence that has a value, whether it's true or false. In maths, statements are either true or false. For example, all multiples of 3 are even. Now we know from previous experiences of proof that we can prove this to be wrong because we can give a counterexample. So all we have to do is to show an example which does not fit in this statement. For example, 9. You can write 9 to be 3 times 3. This means 9 is a multiple of 3. However, 9 is not even. Hence, not all multiples of 3 are even. So we prove this by using proof by counterexample. So basically, this statement is just false, but this one is sort of true. This also brings us to the term negation. Now, negation means when you have a mathematical statement, you can write the opposite of it. For example, all multiples of 3 are even. The negation of this statement is not all multiples of 3 are even. So, in other words, we can write at least one multiple of 3 is odd. It is quite tempting to state, though, that all multiples of 3 are odd or no multiples of 3 are even, which are basically the same thing. But the problem is that we are just looking at the possibility whether all multiples of 3 are even. So even if we have only one multiple of 3, which is not even, we're good. That is the contradiction. This is slightly strong to be a negation because oddness is another state of being for numbers. So I'm not at the moment interested in multiples of 3, all of them being odd or not. I'm just interested in whether all the multiples of 3 are even or not. So if my statement says all multiples of 3 are even, then the negation of this will be not all multiples of 3 are even. If I'm saying not all multiples, I'm opening up the possibility of at least one multiple of 3 being odd. But I'm not bold enough to say that all multiples of 3 are odd. So this is another statement which we can prove by contradiction that it isn't. So let's look at those statements and try to figure out their negations. For example, all poor people are unhappy. Well, regardless of the value of the statement being true or false, we can negate this. We can say, not all poor people are unhappy. So in other words, we can say, there is at least one poor people who is happy. Another example, if P and Q are prime numbers, then PQ plus 1 is a prime number. Now you don't see here stating that all numbers P and Q, all numbers like PQ plus 1, but because we cannot restrict the prime numbers P and Q to be some certain prime numbers but not some certain others, when we are talking about two prime numbers, basically we are picking them randomly among all prime numbers, which are infinitely many. So basically we are talking about two prime numbers here, but these are two prime numbers picked randomly among the set of prime numbers. So actually we are talking about all prime numbers. So in that case, PQ plus 1 is a prime number. Again, if there is such a number, PQ plus 1, again, we are talking about all possible numbers that are in the form of PQ plus 1. Another point is that this is an if-then statement, and when we're trying to write the negation of this statement, we focus on the then part and we try to negate the then part. So I'm going to write the negation of this statement changing the then part only. So the negation will be, if P and Q are prime numbers, I write exactly the same if condition, then there exists a number PQ plus 1 which is not prime. Now I could say if P and Q are prime numbers, then PQ plus 1 is not a prime number. Now this sounds like a negation, but when we state that PQ plus 1 is not a prime number, we're talking about all such numbers in the form of PQ plus 1. And again, this is a bold statement. We have to consider only one number that could exist, and it's not prime. That is the negation. Another example. All numbers of the form 2 to the power of n minus 1 are either prime numbers or multiples of 3. Now, writing a negation of this statement is easy because these are either or sort of statements. All you have to change is to write these as neither nor. Certainly, you also have to play with this one, and you have to say there is at least one number of the form 2 to the n minus 1 that are neither prime numbers nor multiples of 3. So basically the negation of all is there is at least one. This is also the negation of there is no. So we say there is at least one. For example, there is no integer that is prime and a multiple of 3. So the negation of this statement will be, there is at least one integer that is prime and a multiple of 3. Now we can move on to proof by contradiction. Prove that if p squared is even, then p is even. Now first of all, we have to start with assuming that the negation of this is true. Hence, first I'm going to write my assumption that if p squared is even, then p is odd. Remember, we were altering the then part of if-then statements to write the negation. Now, what I'm going to try is to assume that this statement is true and try to show that there is a contradiction. Because if this statement is true, then there's something wrong with whatever we know so far in the field of mathematics. So, let's check if this is true or not. Let's start with p. If p is odd, I can write p as 2n plus 1 for some integer n. It doesn't matter what n is. I can write p as 2n plus 1. And just a reminder that we can write even numbers like q, for example, equals 2m for some integer m, and this denotes an even number, whereas this is an odd number. Now, let's take the square of both sides. So it's going to be p squared equals 2n plus 1 squared, and if we expand the brackets, we're going to end up with 4n squared plus 4n plus 1. Now, just because we see 1 here at the end, we cannot just jump into the conclusion that p squared is also odd, which is true, by the way. P squared is odd because of this. However, it is nicer to show that this is also equal to 2 times 2n squared plus 2n plus 1. Notice that I'm not factorizing this expression. I'm just taking out whatever I need, because now this looks like a number, an integer, 2n squared plus 2n, multiplied by 2 and added 1. This is in the form of, let's say, 2x plus 1, x being this expression here. So this looks like an odd number. So I can now say that p squared is odd. Now, This is what I call a contradiction, because I stated that if p squared is even, then p is odd. And I started with p being odd, but I ended up with p squared being odd. So this is a contradiction. Therefore, we say, if p squared is even, then p is even. So all we have to do is to just copy-paste the statement in the original question right after the word therefore, and this is my final statement. I have to complete my proof with this final statement, otherwise it's going to be incomplete. After that you can say shown or proven better, or in Latin you could say quod erat demonstrandum, which means what was to be shown, literally or basically shown. Another example, prove by contradiction that root 2 is irrational. Now you may see this like prove by contradiction, but you could say duh, I know, but they are saying this because you may come up with proof by counterexample, which we have seen before. That's why they just want to emphasize that you have to use proof by contradiction to prove the statement. So to start my proof, I have to write my assumption, which is the negation of this statement. Square root of 2 is irrational. So my statement will be square root of 2 is rational. So we're going to assume this. And now we can start building upon it by translating this part to maths, meaning square root 2 can be written as a over b for some integers a and b, where b is not 0, because we don't want our number to be undefined. We cannot divide by 0, so b must be a non-zero value. But a can be 0, that's fine. So another thing we have to assume is that a and b are co-prime, meaning a and b do not have any other common factors than 1. In other words, this means a over b is in its simplest form. Now, if we take the square of both sides, we end up with 2 equals a squared over b squared, right? And from here, I can write a squared equals 2 times b squared. Now, this makes a squared an even number because it is in the form of 2 times an integer. So I can say from here that a squared is even. Now, from the previous example, I know that if a squared is even, then a is also even. Now, if a is even, I can write a like 2m for some integer m. If I write this back into here, I'm going to end up with 2m bracket squared equals 2b squared, which means 4m squared equals 2b squared. But you can see that I can simplify both sides of this equation by 2 and ending up with 2m squared equals b squared. This means that b squared is even. But I know if b squared is even, then b is even, right? Because of the previous example. Now, I have a being even and b being even. This implies that 2 is a common factor. Now, we assumed that a and b are co-prime, meaning they only have the common factor 1. Now, I end up with another common factor, which is 2. So this is a contradiction. Therefore, I have to say root 2 is irrational. You see, when you try to use proof by contradiction, your aim is to assume the negation to be true and then try to end up with some of these consequences of this negation being true are contradictory to what we know. Basically, when we assume a statement is true, we try to show that the consequences contradict either what we just assumed or something we already know to be true, or sometimes both. So this is what we call as contradiction. To summarize, all you have to do is to come up with assuming the negation of a given statement. Then you will try to show that this assumption contradicts with whatever we know so far or of the assumption itself. And then you're going to say, therefore, the statement given is true. So let's write the steps of proof by contradiction. So basically, you will be given a statement to prove. You will assume the negation is true, and then you will work on this assumption to show a contradiction. Then you state that this is a contradiction with our assumption, and you write the given statement here. So you assume the negation to be true, and then you show some work to show the contradiction, and you just write this sentence. After that follows the therefore statement. And basically this is how you use proof by contradiction to prove statements. Thanks for watching.